Jösses.
Okay, we're on. Great to see you here. A warm welcome to this third event of the season for Stockholm AI, the second event of Deep Learning in Production. Really great to have you here. This is also the third event that we try out this new streaming and live event. So it's still kind of iterating a bit. Your feedback is greatly appreciated. So is your answering of the questions. It's like 2 questions on this Slido link, where you can also ask questions to the speakers. I will do a brief introduction of Stockholm AI, and then I will hand over to Carl from Epidemic Sound, and then Andjed from King, who will talk a bit about deep learning and production in their respective settings. And then we have time for some Q&A at the end. No? Yeah. So Stockholm AI started out as a meetup a bunch of years ago. But the interest of meetups to discuss AI was quite big, so it grew quite rapidly. And then when it grew big enough, they decided to formalize it in 2017 as a proper nonprofit organization to act as a platform for exchanging knowledge between experts in different fields of AI and relating to AI. We're dedicated to establishing Stockholm as a global player in AI and ML, as well as being the main hub for people working with AI and ML in Stockholm. So we have about 40% researchers and 40% professionals, and then 20% students, roughly, and then some others or general enthusiasts in there as well. And basically Stockholm AI revolves around events like this. And they're normally ranging from technical, which is this type of event, to very, very technical, which is more like academic reading groups and workshop where you work on different problems. We do also have some complementary like business and ethical perspectives as well. But the core is kind of these more technical meetups where we discuss different real life challenges of AI and ML. We couldn't be doing this without our sponsors. So our current sponsors are Ericsson, Peltarian, and Polarmind. So thank you to them. But that's basically the short and sweet introduction. So with that, I'd like to introduce Carl, who will start out. And I should also say that we will have like a 5-minute break between the speakers, so you will have time to run to the restroom at that time.
Nice.
Fire away.
Thank you. All right. Should I look there maybe? I don't know. Poof, poof, poof. Okay. Hello. I am going to talk a bit about similarity search on the music based on audio as features. And then I'm probably going to ramble a bit about random stuff and have my own opinion, and then we can argue about it, like why use deep learning in tech companies and how. There's good ways of using AI and bad ways of using it, and I have complaints about certain things. But okay, so the fun part today is just to maybe demo a deep learning model we've built now to helping YouTubers finding background music for their tracks, and potentially in the future even sound effects. And my primary interest in being here, aside from this being fun, is to kind of get your take on how we've built what we built, and also what we built, like future potential in that and stuff. And obligatory kind of who we are. So I like to do music programming stuff. Building synths would be a fantastic thing to spend your life on, I feel. Playing guitar and computer programming and music technology, all of these things kind of connect in my head. And machine learning feels like an obvious next step for music production. And then now I'm at Epidemic Sound, which is a company that has a lot of audio data, especially musical audio and sound effects. And the business idea behind Epidemic Sound is then to help YouTubers and storytellers, maybe TikTok, Twitch, etc., find easy to use music tracks. And that's something that's hard to understand. Like, why does that need to exist? You can just download MP3 files, right? But if you do that and put it up on YouTube, you will get demonetized or get a copyright claim on all of these things. So the idea behind this has been historically that the music industry is very strict about legal requirements. It's very hard to find even the stakeholders. I want to use your track, but who are you? You're someone in Germany and there's some other person in the Netherlands, and I have to pay all those different stakeholders. And it's a bit of a mess. And I guess the music industry and that structure predates the internet. So now, of course, it should be easy. And that's where these kind of business ideas fits in. And to do this, we have our own music, which then we offer subscribers to use in their YouTube videos. And within this little thing then, okay, we have a lot of music data, great. Then we want to do some machine learning, I feel. So we have this team now at Epidemic Sound, where we're trying to really build intelligent product features on top of data-driven methods. And it sounds very fluffy, but it is quite obvious when you see it. And the goal for us would be to kind of use machine learning in a responsible way to create improved search experiences or browsing, and potentially even modifying tracks and adding versions of them, etc. Arguably, though, I don't think we will ever kind of go for like generating music. I don't think that makes sense, honestly. But I think adjusting music in the hands of a human, that would be very powerful. And this we can argue about. Yeah, so some project we have, and we have been doing, is like you can extract track metadata from a given audio file. Pretty convenient, like give me an MP3 into a browse into the catalog so you can browse easier. And then this it would be very convenient if a user could find similar sounding tracks, not based on what it's called, but based on how it sounds. For deep learning people, that sounds obvious. In the next phase, I think we're going to look more also at like saying, based on what videos you make, could we give some suggestions on how you should use your sound effects in a cut, or maybe high contrast, black and white, it fits with film noir, maybe jazz songs. Like there's probably some redundant overlapping information. And looking at that mapping, I think is very powerful for us as well. Although we haven't really started with that yet. So this will be the topic for today, audio similarity. Okay. So as I said then, the overarching idea could really be that I don't know what someone calls a music libraries, genres, moods, etc. It's hard to find words for music sometimes. So I just want to browse by examples. And we had some we had some use cases for this in the product ideation. So particularly these, I think. Do you have anything that sounds more like this? And that kind of question is very common. It's also important to keep in mind that like a YouTuber isn't necessarily a musician, so they don't know musical terminology, while the people working in the company that puts up the music, they use musical terminology. So this might be very convenient then to just circumvent all of this. And okay, let's try to demo this. We'll see. Okay, and now let's do a little sound test. So I will try to find some music on this website. Hopefully this goes out into the screen on the Thomé live. If it doesn't, we just look at us being very awkward now. That's okay. Let's see. Okay, so someone maybe shout the genre. Pick a musical genre or something.
Music.
No. I think we actually have music, but okay, let's go for music. Let's see if I can find it. You don't want to see pop? I heard music. Okay, I clicked on music. Okay. But okay, so what can happen for users now is that they end up in a track page. They have a sound, a starting point, and it sounds like something. And this is not cherry picked, so I hope this nearest neighbor now in this lookup in this deep learning model is actually similar. We'll see. Oh, that's pretty okay, right? Arguably similar. So to give some contrast, right? If I turned off the audio-based embedding learning thing that I'm going to go through soon, and just learned, we had like a find similar, but it was based on tags, so similar mood and matches then in terms of genre labels. And then the nearest neighbor to this track is a query. Same artist would probably work, but let's look at that one. That's even a bug, I would say. This is the same track, it's just an instrumental version, so oops. But we take the next neighbor. Is this similar? Okay. In this case, I guess for this type of music, it is kind of similar with tag-based, so hybrid approaches will be very powerful. We could take some similar, let's see, what's a good one? Do you have a good artist? Gruvfrun, I don't know. Maybe this. Oh, okay, this is good. Okay, so here we see different sections, right? So it could be that I really like the last part of the song. Let's skip the first artist, it's the same artist. Okay, so that's not so. Okay, but the point that I'm trying to demo here is that if I had instead said that I only really care about the intro in this, I want more like the intro. And I think this is maybe the point that we want to make is if I only like this part, I don't like the outro so much. Is there a Swedish radio? What? I'm sure we don't have any neighbors with particularly that Swedish radio thing, but maybe this is. So that's kind of where it makes sense to me that you say, I like the chill out beaty kind of thing, but not the drums. And let's do one more something for maybe this one. This is a good one. Okay. Oh, sorry, I got lost. Okay. Oh. Okay, it's kind of similar, it's different rhythm. We know this, we're tweaking the similarity. Rhythm might matter more than we think. Arguably similar vibe in terms of YouTube videos. I want to have something in the background that sounds and feels similar. And again, like let's turn off and go by just tags, and let's ignore the same artist because this artist is a specific kind of sound. They will all sound similar, and that's good. Went to the next artist, but that's not the same because that heuristic is quite powerful. Hopefully this sounds similar in the tag-based space. And I guess that's where it kind of becomes tricky. That's modern jazz. Why does that even pop up so high in the tag-based? I'm just clicking around. It's kind of fun. I can send out a link later and you can click around and see like when does this similarity search work well and when does it fail. One thing we're looking at is like, okay, when we don't have any neighbors, what do we offer the user? Now we're just taking the nearest always. But in the back end, you're going to see like, oh, that distance was far because we don't have any matches. We don't have everything. Maybe these genres were a bit tricky to demo. But again, let's do a little back to the audio-based one. So maybe I like the fade out. I don't know. Fade out. for some reason in my video I need that sound, but I don't want this one, I want a different one. Okay, let's say next nearest neighbor. No, I don't want that one for my video either. I want this one. And then I let's download that one and use that in my video and stuff. And I hope this kind of demonstrates like this could be a very powerful way of searching. Like, I don't know what this is called. You call it like fading out on trumpet, whatever, just that thing, but more like it. And this is just the beginning for us. We're gonna dig into some details now. Ooh, poof, back. So the basic principle here is quite easy. I mean, intuitively, this makes sense. What we're saying is we want to find some space where the similar perceived sounding things end up close, and sounds that sound not similar, they're far. And then we could use that measure and just measure distances and do nearest neighbor lookups and so on. So the name of the game is here to find this metric space that we can then use for this. And to do that, we're kind of using now music production knowledge, which I think is quite cool. So I'm going to show you more about the details of this model and this system. But the cool thing is that we can kind of git commit how we say music sounds similar to other music. So if someone changes their mind, like a product owner or us in the machine learning team, you know, a new version, you git commit some other assumptions, and the connection between the inputs and the targets in this kind of machine learning setup is explicit. So no one needs to kind of guess like, oh, who annotated the data? We don't really have that problem here. And buzzwordy kind of thing, you could call this kind of self-supervised. But I think the important part to push is that we get it explicitly in code. What is similarity for us? Or like, okay, you can look here. And then we can have different variants and we can tweak them over time. And if, I guess most people have seen triplet loss, but it's basically this, then you want to minimize the distance from a known reference to its annotated similar clip. And you want to also maximize the distance from the same reference to something we say is not similar. But you don't only want to do that, because then you might collapse to many pretty bad solutions. So we also say that these kind of loss terms compete. You don't maximize both and minimize both. You just make sure that it's enough that the negative example is further away than the positive example. And that's all you need. And that's kind of why this hinge loss pops in here, and why this little margin, this alpha for the margin, is important when you hyperparameter tune. But it's really just that intuition. You want, like, from a given audio clip, the things that I say sound similar should be a little bit closer in the embedding space that we're trying to learn than something I say should not be similar. And there's a lot of theory on this. Within this, we're doing then, we need to find this kind of like examples. So we have a big catalog of examples. We have some audio clips from our music library, music catalog. And then we create the positives. And this is kind of maybe the cool part where this becomes like we can encode invariants. One example could be like a song that sounds the same even if it's a different key, maybe. If I pitch shift it up a little bit, it's going to still feel the same in a YouTube video. So let's say we assume that we write it down in code and we find positives with that transformation. And for finding the negative examples that should be far away from specific anchors or references, audio clips, we can just use track metadata. So for example, a good heuristic to use here is if a track, or if an audio clip comes from the same track, it probably sounds very similar. If it's from another track, it's probably not so similar sounding. And even more so if it's from a different genre or different artist, etc., etc. So we just add all of these loss terms, and then they can compete a little bit. And again, then, so finding the transformations, the positives. One example I said was that we could pick an audio track, a 3-minute song, pop song, pick a 10-second snippet from it, and say that it should probably be embedded close to another 10-second from the same song. That's a pretty good starting point. And we use this quite a bit. The hypers around this are tricky, but the intuition is easy. Similarly with like shifting the pitch, you can maybe slow it down a little bit, make it a little faster. Maybe, this depends. And as you maybe noticed in my little live demo thingy, rhythm might be way more important, I think, for our perception of similarity than these rows are making it sound like. maybe I would like double and half the tempo rather than slowing it down 20%, because then it's going to feel very different, I think. Adding some reverb could be the same. Like maybe not. If you don't approve of it, you can do a Git branch, feature branch, add your own augmentations. And then some noises, maybe just for fun, but we could also do like distortion or something more musical, to say like, oh, it's a metal song with slightly more distortion, that's still the same. And as I'm trying to push here, there's a lot of design potential in this, and this is really like design. You can design the similarity notion by these kind of augmentations. And these are things then that the model would, by the data, the model would maybe be invariant to these kind of transformations, because that's the objective we're giving it. And speaking of the model, how am I on time? Is it? Cool. So model design, it's not so interesting, honestly. Like you've heard people say this before, but we picked something. It's a ComNet, and it's good. It's like all of this, as long as it's expressive enough that you have some room to overfit your training data. No. And we do some kind of traditional things. Focus on monophonic audio currently. I think we want to very quickly make it stereophonic. That's a big aspect of perceived music similarity. Certain genres are only based on like being a very nice spatial imaging. But I mean, baby steps. We're doing 16 kilohertz, could be CD quality instead, but it's just a matter of compute costs. So these are quite normal kind of hyperparameters. We do log-mel spectrograms, also quite standard today. It's that you make everything into a time frequency representation. We don't take just a little sparse audio signal and work on that directly, again, for kind of computational costs and convenience, and some slight time invariance baked into that feature representation. And as I said, so ComNet, there's a bunch. We take all of them, we try some of them, whatever gives good numbers on metrics or in user tests. I guess we stick on that one. So in some way, we kind of just landed on these numbers. And there's, again, we could explore this a lot. There's also an important nuance in triplet losses when you compute the loss for a triplet. And it could be that you actually allow the negative to be within a little margin. It's not that, the only constraint isn't that the negative is further away than the positive. It should be a little bit even further away. And that is also something you can play with. There's a bunch of different triplet losses, and not even mention contrastive loss in general. We do add them, 32 clips. There's also, oh, maybe this one is actually good, some like hidden insights that we got from Sebastian over there. It's bumping the mini batch size when doing online triplet mining. Very good bang for your buck. So 32 is slim, the small. 512 would be great. And that falls down to like GPU VRAM. But yeah. And not to just like build deep learning models for the sake of it, but we also start, of course, with baselines. So the silly approach would be to say, given an audio clip, we will produce a random vector for it. And then we will see if that happens to cluster in the same way as our metadata. That's our metric. And to give some context around that. When you've got a good encoder of music that puts stuff in near each other when it sounds similar, we don't have that number. We can't run that, of course. We don't have human ears in a Python script. So we're using side information as genres or moods or BPM. And we're saying, hopefully the encoder puts audio clips that are in the same genre in roughly the same cluster. That's a way of making model selection possible offline. But if we get a perfect score on those, we haven't really achieved anything. Then we would just use the tag-based version. So here we want a number in between 0 and 1, which is very tricky. But for the baseline approach, it's, I mean, random is random. We just want to see that like if everything is film, I mean, you actually get a clustering of those random embeddings that kind of works with that side information. That's a good to know. And then we could also do a normal like shallow learning approach with now we're doing like MFCC vectors and then a little PCA on that, and like that's cheap and easy and simple. And is it worth it to do this big kind of TensorFlow thing? And in these metrics it is, and also in user testing it is. So yeah, let's ignore mean average precision. That's good. Okay, if you're interested in tech setups, how we work, I think this is maybe our strength in our team. We're pretty interested in Google Cloud. We only use Google Cloud now. And I've been a proponent of TFDS. I think it's pretty good. Also, I made these diagrams, now I have to show it to you. I spent time on it. But we have a little human in the loop. And here's where I would love to get some inputs. Like, we're spending a lot of time running these different steps. We have a data warehouse at Epidemic Sound. It's based in BigQuery. We have all of our audio files. They're backed by Google Storage and also S3. It's like nothing super strange. We zip them together into workable binary data that we like for our TensorFlow things, and that's TFDS or TF records currently. I would love to have something else there, perhaps, that's more ad hoc queryable. But we render these data sets, and then we sit in a little feedback loop with ourselves, start scripts on AI platform, and then I mean like ML Engine, the old AI platform. And we're looking at Vertex like everyone. And maybe the coolest thing here, actually, is how this web app was quite fast. And that's based on putting the embeddings into Elastic Cloud, which I think is a very smart choice by my colleague over there, that we got this performant for quite little effort comparatively. So you can add new tracks without taking everything down, and then they will pop up, because we're using Elasticsearch queries for finding the nearest neighbors in the 128 dimensional space. And that's a feature in Elastic, so that's pretty cool. There's other solutions for that too, of course, but we already had Elastic. Yeah, this is pretty standard. And maybe the more important bits, I think. Okay, so doing this, it's super hard to write NumPy, TensorFlow, PyTorch, whatever. Like, it's stupendously bug prone. And when you do it, you don't even see that you've done it. You just get numbers out and the program runs, it works, but it's not right, and you will get bad predictions, but you can't see that in your program because it's not technically system failures, it's bad numbers. And so the only way out of this, as far as I know, is that you can have peers, and that we work kind of closely and get like really good skeptical eyes on it. Like, is this the right optimization here? Like, we've had so many silly bugs. Like, I think like the hyperparameters was like 1 minus the probability for a while. And it's like, oh, but that's fine, because we had 0.5, so no one noticed until Oscar noticed, and small things. Well, I had like the same random seed for all mini batches, because with TF function, it was serialized up front when constructing the model, not when running the forward pass. Gives a really bad model prediction thing, like all of these things. I think it's really currently, it's down to like in developing models, algorithms, peers, peer review, kind of very detailed views on it, and very skeptical is the best. Only way really I know of currently. We'll see in the future. But these two dudes, very good collaborators, I have to say. And maybe to promote this collaboration, we're also trying something at Epidemic Sound now, which is that we want to kind of encourage and even enforce that people kind of knowledge share early in their projects, don't spend 2 years on a model that never goes anywhere. So we want to do kind of like do a little bit of everything at once, a vertical slice then from game development. You do a small subset of data, perhaps a smaller, easier model, whatever, in a notebook so much. You don't need to think about Kubernetes yet. Establish baseline metrics, baseline methods, and do the literature study, all of those bits in a time box, and knowledge share with your peers. And this is just a hunch. I think this is going to be powerful. We're practicing this kind of workflow of saying, like, when you start a new project that's more R&D-esque, you're expected to invite your peers to a future presentation in about 1 month, where you show them what you've done and what you've established in terms of, could this go into production? Will this make our users happy? And answering that question, I would like to kind of take that early rather than 2 years later in a project. As we probably all know in this room, we've seen many projects just going on and on and on. Good solutions to unimportant problems is very common. When we had a pre-study in this work, and then we started with 1, and we only had 1. I think in the future we should maybe have 2. We should have 1 for the literature review, and it's like, yeah, I've seen people do this. I think we can do this too. That should happen really early. And then you should do, yeah, we also tried it. We took a little data. We got these numbers. They look really bad, so we will not proceed. Oh, okay. Good to know. So I think we're going to split our pre-study into 2 presentations. But yeah, the current best thinking of how to get deep learning models to be anything useful. And final things. No one invents anything. Everything exists. We always stand on existing things. These papers are amazing. You can read them multiple times. I still kind of, like the third one, I've read 10 times. I kind of understand the background, kind of. There's a lot of depth to similarity learning. So I want to just really highlight that these references are amazing. Like dig into them. Basically what I demoed is actually the first paper here, but we did it on music, not just general audio, so like cat meows and dog barks. So it's very similar and slightly different domain knowledge, of course, like pitch shifting a dog bark might make it a different class. But yeah, these are good. Check them out, I think. And otherwise, this is it. And if you want to work on this, we need people. Everyone needs people, but we really want people. And if you like music informatics, especially, that's a relevant area for us. But with that said, we also have people working now on growth, like LTV modeling and churn and all of these areas of a business as well. And also, if you don't even care about machine learning, we also want to have more full stack developers. So Epidemic Sound is kind of adding a lot of people. And me, you can find on RML, where I write silly things that make no sense. And add me. Could be fun to do a lunch or something and talk about next steps. Thank you.
Thank you so much. That was really awesome. I think we'll have you back for the Q&A session at the end. And we'll welcome up. So from, one interesting area of deep learning in productions to another. I guess you can introduce yourself a bit more.
Thank you. So, that was technical. Yeah. So, hello and welcome everybody. My name is Mohammad Hussein Andjedani, in short Anjed. I'm principal MLOps engineer from MLOps team at King, and my colleagues and I are currently trying to build an end-to-end machine learning platform that supposed to support and facilitate AI projects for various teams across the company. Our team used to be a part of another team which is called ML R&D, okay? And after a while, these two teams, we formed two teams, and we are now sister team to ML R&D team, and we are working closely together. I'm excited to be here with you to share some of the challenges that we faced during our attempt to shape an AI-powered content automation system. This is a little bit tricky because I need to move forward on both laptops. So without any further ado, let's see what's waiting for us today. This is the outline of my presentation. It is color-coded with our company's core values. The core values you can see on the left side. And there's a sixth one, which will be a surprise at the end. So we are going to walk through together the story of the content automation at King. The story of our bots and robots fell in love with the candies and started to crush them. It happens in 3 episodes, but before jumping into the story, we will have a prologue and we will be familiarized with the concept of content and content automation at King. And then we will have a trailer as well, obviously. And we will have a quick look at what is the final state and current state of candies and bots, and what are the final artifacts right now. The first episode will take us to the genesis of the bots and the origins of the idea. After that, the second episode in blue for Fast and Fluid unfolds how the notion of bots and automated playtesting gained traction and was adopted within the company. In second episode, we will go through many challenges in building a platform, a working piece of software, which is scalable and reliable and can perform automatic playtesting. And at the same time, it is suitable for experimentation and R&D. The third episode tells how this army of bots unleashes the power of power for doing content tweaking and other use cases as well. So, what is it about content? I guess almost everybody knows King's most famous franchise, Candy Crush Saga, and yeah, it's a syncing problem. And how is it available on almost every device and everywhere around the world? We have developed around 200 games so far, and we have around 250 million monthly active users. All these games are under 4 global franchises and also new games, which I highly recommend to try this one, Crash Bandicoot and Run. It's really fun. And it's somehow different from our other games. So we have large families of games. Each game has a world, tens of thousands of levels. Where are we? I guess I skipped. Yep. Okay. It's a little bit complicated. We have the board for the game. It has a geometry. We have enormous amount of game element types, blockers, boosters, charms, and on top of that, move limits. You have a limited number of moves, and of course, different objectives for the game. All of these are contents. So creating new content and managing content is a very challenging task. It's really hard to keep up and produce fresh content for the users. You may have noticed that we are producing nearly 30 levels per week for live games. And recently, Candy Crush Saga has announced the 10,000 level. Yeah, that's a lot, I know. The tricky part, the tricky part in producing this much content is that all this content are fresh or new. They are never exposed to the real players. So we need a way to find out whether this new content fits the journey, the whole journey for the game. And is it fun to play? It's most important one. And does it overall provide a good user experience? In order to do this, we have a life cycle for content generation in place. First, level designers create content, and there's a long period for balancing that content. It will go many times through this tweak and feedback loop until it meets the required KPI. But unfortunately, it takes time. It's boring most of the times. In addition, we will do only a few game rounds within the timeline. But with automated playtestings, I may sync my slides, sorry. With automated playtesting, many of these problems will be solved. Automated playtesting in general refers to the effort of automating parts of the iterative process of adjusting game and its parameters and testing them by simulating gameplay with these parameters. The idea here is to automate playtesting via a virtual player, like an agent or a bot or any kind of algorithm that plays a level autonomously multiple times and provides needed statistical feedback for adjusting that level. And this will relieve our level designers and QA from long and repetitive rounds of gameplay and playtesting, and enables them to focus on the creative part of their job, to design new exciting content. And we will see that in addition, having a good playtesting platform in hand will enable much more exciting use cases, such as automated tweaking. But the important thing is that we need a bot that plays like human, not a champion, because algorithms can perform in most of the cases much better than human in these simple tasks. The tricky part here is that we need a human-like bot. So what is the state of the art, what we have built so far? These are the main things that we have built. First, we have a level AI SDK, which both supports supervised learning and reinforcement learning. And on top of that, we have built a playtesting platform that uses that SDK, and we will see that basically it's an industrial level playtesting platform, and sandboxes for scaling experiments, and the tweaking engine and the tweaking platform. This is the timeline. This is the journey that we went through to build all these. Back in 2016, we had heuristic and evolutionary algorithms. Then, after that, we started to conduct some research on supervised learning, and we sent those supervised learning bots to production, so kind of production. I will explain later. And after that, we started to do some research on reinforcement learning, and after that, content generation and content production platform. We did a POC and content tweaking, and in 2021, we had the content sandboxes and tweaking platform. This is a really high-level this diagram for Level AI SDK, the SDK that I mentioned earlier. Level AI SDK is our development kit for all work around AI bots and playtesting. Our requirement here was first managing game environments and store and handle game state and action processing, and support gameplay heuristics, and then running supervised learning and reinforcement learning agents, as well as training runners to standardize how we run and analyze the training of new models, for both reinforcement learning and supervised learning, and inference runners, in addition to training runners that support heuristics, supervised learning, and reinforcement learning, because heuristics don't need training that much. We decided to put these output of these bots into BigQuery. So these runners need to put output of all these into BigQuery, and we needed to standardize this process. And we need tooling that help to formalize and standardize in all of these requirements that I mentioned. So to cover these requirements, we designed Level AI SDK, as you see. The component on the right side of screen, Level AI Agents, is responsible for gathering all the different playtesting agents that are meant to interact with each of the games supported in our environment component. So basically we have, for example, supervised learning reinforcement learning, or heuristic agents. All of them are standardized in the Level AI agents component. The next component is content feature extractor in the middle of screen. It is a series of utilities that help representing board states for the games. Current state of the board and the features on the board, which I will show you later. It has many layers that describe the current state of the game board. And this moving part is responsible for those. Also, we have Level AI core, which is round thing in the top here. It is a set of helper functionalities and abstractions that is common across all other components. And this way, we are trying to create a common language between these components and to prevent them to deviate from each other in the future. So they follow same principles. It is the core part. And Level AI service, which is this one, is a set of APIs that is deployed in two forms. One of them as a central API to create configs needed for running all the agents. And in another role, it plays as a distributed POP subscriber, which handles the communications between all these parts. Also, we have offline validation, this one, which allows scheduling cloud data flow jobs. This data flow jobs serve the purpose of being able to evaluate the playtesting bot against a given set of input states using a series of pre-built or custom metrics. Okay. And in addition, we have Level AI environments here that hosts all game environments that are currently supported for supervised learning and reinforcement learning or heuristic agent interactions. It keeps a track of the environment for the game. So when you're doing the automated playtesting, you need to track how the environment of the game reacts to you, and this moving part is responsible for that. So on top of Level AI SDK, we built this platform, which is called playtesting platform. This platform is hosted in Google Cloud and benefits from being cloud native. Our models are built in TensorFlow. We can access player data from BigQuery. And yes, it is also here. And for reinforcement learning during training agent, our agent is directly interacting with the game build itself, which is deployed in our bot ecosystem. And as you may see here, the player data comes from BigQuery. Our bots are trained here. Models are saved in Google Cloud Storage. Inference also happens here. And we have toolings from ourselves and other parts of company. For example, we have something called DataLand in our company that is a platform based on notebooks that serves our data scientists and has most of our common tools inside it. So this is playtesting platform, and also we have sandboxes. There is this usual conflict between requirements of R&D environments and production environments. So we built a sandbox that is basically a playground that replicates the production services in a semi-isolated environment that allows the researchers and data scientists to do their experiments at scale. And in the cool thing about the sandboxes is that they are most similar to our real production environment, and data scientists can have a good experience of what will happen in the real scenarios. I will come back to this later and describe how it works. And after all of this, we have our tweaking platform. This is a particular one from those many use cases that I told you that having playtesting bots platform will enable. I'd like to share this one with you. The goal of tweaking is to improve the content quality. We want to make our content, both legacy content and new content, compatible with the design guidelines. Okay. For this purpose, we have built this tweaking platform that is an evolutionary solution that automatically tweaks levels. It is a genetic algorithm that generates a population of candidates. Each of them has a slight difference from the original level and plays all those levels against the game engine through the playtesting bots, collects the results, statistical results for playtesting, and decides for the next generation, and does this iteratively. After doing it for enough iterations, it can recommend, for example, 5 candidates, 5 little tweaks to the level. That makes it better with respect to our KPIs that measure the performance of a level. So let's go into the story. Okay, I will go faster. Our first approach was a heuristic approach. It just discovers the weight for the moves automatically and ranks the moves with respect to that weights and just does the best move. It is the same thing that if you have played Candy, it starts to blink if you don't move for some seconds. It starts to recommend to you that you can do this. You can switch these ones. But the heuristic it has obvious drawbacks. It's not general. It's very level specific. It is very game specific and not flexible enough to build a bot that can play against all levels. So next strategy was Monte Carlo research, which is a very common approach that has zero knowledge of the game and simulates the gameplay, and it is accurate enough, but it is intensive when it comes to computation. It is slow, so it's not practical. All we need is a bot per game with better AI method, automation, and iteration. So we started to do research on supervised learning. We have large number of labeled observation. By observation, I mean player data, which is a state of a board and the decision that human agent made for that specific state. And we use them as training data, and we can predict unseen observations, new observations that bot face them. So far, we have tested CNN-based and ResNet-based methods. We are encoding our state of the game through stacked representation of matrices of each of them holding binary description for one element of the game. For example, you may see here that A layer holds red candies, a layer holds blockers, green ones, blue ones. This is 9 by 9 by around 100 tensor. And the outcome is a category of moves, 144 possible moves, eliminating the symmetries. 144 moves that each of them represent, for example, if this category is selected, this one 141, it means that the cell above and below this will be switched. Okay, the neural network works like this. The observations are these tensors and labels are this. So we got a good results out of our supervised learning bots, and now it's time to have a good army of them. Now we can have lots of them to do playtesting. Very first version was a POC, and almost no one knows about it, but it was something on-premise in the King infrastructure, and it returns to, I guess, 2016. And in this stage, we have done, apparently we have done just a POC and deployed bots into work, but it's not real production. As I heard, there was some Slack pings and emails, give me this JSON file, or I will do this, I will put this one there. The kind of manual things that you do during a proof of concept process. So, but next version was more serious. Actually, it was really serious because now we have a cluster of a Kubernetes cluster in place that can orchestrate and auto-scale the computation for game rounds. And everything else was done inside the King's infrastructure, the API server, and other moving parts. Maybe it worked here. This version was actually the first working version in production, and there was a couple of issues in this architecture. One of them is that Kafka and Arbia didn't satisfy the required KPI for playtesting in this manner. And on top of that, these tools are not data scientist friendly. So we needed to wrap them inside another moving part that some ETLs that bring data into data scientist friendly environment that fits other components. Also, having just computation in Kubernetes, it was impossible to track the bugs that happened and reproduce the conditions that were needed to study the problem more accurate. It's a critical thing to be able to reproduce the state that the bad thing happened. So this architecture needs Somber to keep track of the process and keep the metadata for that process. Another thing is that when things become serious, you need to think about different kind of problems. For example, you need to be more aware of SRE specific things. For example, one thing that we had for this is introducing infrastructure as a code via Terraform. Or this part, archiver and cloud storage, is the part that is responsible for keeping track of experiments and reproducing the states. Also, we replaced this Redis and BigQuery and the pipelines around this for addressing the issue that happened with Kafka and Arbia. Arbia is, by the way, Arbia is rule-based event aggregator, is an in-house tool that King built, and there's a full blog post on our technical blog. And the more interesting thing in this version 3, is that we take the advantage of our ML serving platform, which is one of first parts of our ML platform that is outside bots scope. It is a general thing in the company that is responsible for serving machine learning models. We took advantage of this moving part as well. So this is the state of the art for playtesting bots. One interesting moving part in our playtesting bots is ETL pipelines. That they work like this. First, we will create configuration data, and we will put them in Google Cloud Storage. After that, a data runner runs the data collection job according to that config that we created before, collects data, puts them into BigQuery, and after that, those data flow jobs will take data out from BigQuery and convert them to real TF records that are used for training models. And this is level AA SDK in action for training. The green parts are specific to supervised learning, and red part is specific to reinforcement learning. This is the config store that keeps configurations for the gameplays, and data sets that we saw in the previous slide here are kept here. So they are connected to our training runners, and the same thing happens for inference. So this was our play testing platform, and I told you before that we have an exciting thing called content tweaking. This complex diagram shows how content tweaking works, but most important and most interesting part is what happens inside this box. During deployment of our content tweaking platform, we faced some interesting challenges. Consider a level that is being tweaked in our tweaking platform. The tweaking engine creates, let's say, 100 candidates. Each of them needs to be playtested 1,000 times. This means 100,000 game rounds. And this may happen 100 times for a single level. And at the same time, you can have tens of levels being scheduled for tweaking by level designers. So if you do the math, you will find out that we will face hundreds of millions of game rounds at the same time. And the other thing is that tweaking engine, the genetic algorithm, is a time-consuming and computationally intensive task itself, and inference from our playtesting bots is also a computationally intensive task, but at a different scale. And now imagine there comes a bug. There's a hiccup in network. Something fails out of nowhere. And what happens if you lose all the job that you have done? You will lose hundreds of valuable CPU time. Okay, and you need to keep your users, level designers, waiting for the shiny new Twix, maybe for 2 more days. So we needed to be careful to do the architecture for this part. We decided to use event-driven architecture and asynchronous communication to decouple the genetic algorithm from playtesting bots and allow them to scale independently. And also we were able to separate the stateful parts from a stateless parts and keep track of the things that are happening. And in this manner, we will be able to continue if something fails for any reasons. The lesson that we've learned here that is you don't have to follow the normal guidelines when you have an unusual use case. You need to tailor your custom solution. And also we have sandboxes. I'm going over time. Sorry for that. We have sandboxes here, which worth mentioning. We've built this in Argo workflow and Argo CD. As I mentioned before, these sandboxes have everything from production environment. Actually, they share their pops up event bus and the bucket storage, Google Cloud Storage, and the BigQuery projects with the real production environment. And they have their own Google Kubernetes node pool. In this way, you can track the amount of resource that you have allocated for research. Has its own Kubernetes namespace and content inside that, and MySQL database and Redis cache. These are sandbox specific, and there are things that are shared between sandboxes but not shared with the production. So it went like an economic choice. So we tried to reuse everything that is possible to reuse, but when it comes to production red lines, no, we will create a sandbox specific. But is it possible to share that thing between the sandboxes? If yes, we will do that. If not, we will spin up a sandbox specific instance specific thing. So in summary, what we have learned from our journey is that take good care of your data pipelines. One thing that I didn't mention during my presentation is that our customers, which are game teams, ruined our data many times with new releases and change of contracts. Also, take good care of your metadata. For example, versions or data about the things that happened inside your platform. Those things will help you a lot in future experiments. And starting simple with a very, very simple solution is a good idea. And in this case, because the machine learning pipelines are not just any software product, and they're more complex, it is best to avoid premature optimization. Try to optimize when it is really critical to optimize. And it is also important to review your requirements and architecture occasionally. And embrace the synergy from other parts of your organization. If there's a tool that can help you, it is really encouraged to use that. And establish a good relation with your stakeholders. For example, in our case, game teams, Candy Crush team is an important stakeholder in our journey. But most important is that in my opinion, AI maturity is bound to your organization's adoption and tech maturity and literacy. Like they say, the apple never falls far from the tree. So if your organization has limitations on technology or literacy around data or AI, it will bound you. Try to expand there. We are hiring. Yes, join us. We are trying to make work playful. And yes, thank you.
Thank you, Amjad. I think we'll do our promised 5 minutes break now, and then we'll come back at 7:20 for some Q&A. And we're back. Welcome back. Hope you had enough time to do everything you needed to do. I'd like to bring up Martha to moderate our Q&A session. So I hope you all post your questions on Slido. If you didn't, you can still do that. I'm not sure if we have the, yeah, maybe we have the Slido code.
I can say
I can
it,
shout it out.
or
in a
you
bit.
can shout that because I don't have it here. But maybe Andjet and Carl, you can come up as well. You don't need to sit down. Ingrid, do you have the code? Okay. But I can see it here. So it's U695. So for your online or if you want to ask more questions, and it's good if you also say to whom you are referring to. But I have some, I can start with the questions for you, Carl. So this sounds pretty novel. Did you take inspiration from any previous academic work or practical applications?
Yes, of course. I mean, the references at the end, naturally. So that John Hershey Danellis paper on general audio representations, I think, yes. And but also like self-supervision is up and coming, and those ideas are applied in other modalities. So it makes sense to just do the same thing, but for audio and music, kind of. I don't know. Feels like a tricky question.
You cannot say no.
No, it was weird. But again, like no one ever invents anything. It's always iterations on existing ideas, right? That's just fair and true. So,
okay.
No.
Great. How do you plan on handling multiple versions of each model?
Beyond like the obvious A/B testing thing where we want to see what people click on, and then just pick the one that gives the most clicks. That's not maybe the interesting part. So I'm personally very interested in control of saying like I only care about the drums or the rhythm, or I absolutely care about reverb. I don't want you to say that reverb does not matter for my use case. So in prototypes we have internally, there's going to be more like check boxes or some slider or some radio button where you maybe choose, and then we just in the backend train different model setups. That's easy peasy, really. And if that should be a shared embedding space or separate embedding spaces, that's kind of unknown. So I don't know if anyone has a good kind of no, you should definitely do this. Please let us know.
I don't.
No.
I'm sorry. Let's see. When extracting the spectrograms, are you using the entire song or only a subset of it, like 30 seconds?
That's a pretty good question, I think. We don't take the whole audio clip, also the whole audio track, because they have different lengths. Some can be 5 minutes, some are maybe 1 minute. So then you need to do something, right? It's going to be a mini batch. So you need to cut them off or pad with silence or do something. So we just kind of default to saying, no, really random crops, as in computer vision, random clips, random excerpts from a track of a fixed length. So we circumvent that problem. And the nice side effect of that is that we also balance kind of a data set then, because if a track is very long, that doesn't necessarily mean that it should be way more prevalent in training data. So we take like 10 random excerpts per track. So the long track will we're going to miss some material in the raw data, and I think that's okay. But it's a question like, should we do 20 random crops? Maybe that's going to give us even better metrics. Not sure.
Have you decided on how many random crops?
I wrote 1 0 because 10 looked nice instead of like 8 or 16 or 32.
Okay.
But it keeps being a hyperparameter in our data flow jobs where it's like, do we want to double the size of the artifacts, and not necessarily the training time, that might not be doubled, but at least the number of gigabytes we store. If it's like 200, 300 now or something, double that. Like, is that the most bang for your buck kind of question? I don't know. Someone's gonna start that job sometime.
Okay. Martinas asks, I might have missed it, but what is the size of your music library, and how would the similarity model scale, assuming the library is growing?
So like, if we need to retrain every week or every day or stuff, like is it the concept drift thing? Perhaps could be the question. There's also I mean, in terms of representation, the catalog is more important than the number of tracks. But the size of the raw data would be a couple of terabytes. And then it's like 40,000 or something independent tracks, but some of them come from the same artist, so they might sound very similar. So it's not fair to say that that's an entirely separate set of statistics. But I don't know. Okay, so if someone makes a new genre for all of a sudden, a new music trend, will this kind of existing encoder generalize to that? Probably not. I wouldn't assume it anyway. It would be very strange.
All right.
But we kind of down prioritized retraining. It doesn't feel so important. Feel is the keyword. I don't know.
And we'll see what
Yeah, we
happens.
will.
Going for a Shazam interface. No, that's not the right tone. Going for a Shazam interface so you can hum what you're looking for?
So like recording your own audio is the question, or?
I guess so. That's what
Yeah.
I understand.
So that's gonna be probably the next kind of prelude. So this model is kind of cool. We have different product features on top of it we want to do, and that's one of them. And already one of our colleagues, Daniel, started building that on an iPhone app for fun, and they like demoing it to his kids and stuff. And he had some feedback about like surprisingly this existing encoder does generalize okay to someone playing guitar in their apartment or whatever. It's gonna find solo guitar, so that's great.
Okay.
But it did not work so well when they just like had speakers playing an existing Epidemic sound track on his laptop speakers. He's recording it with his iPhone, and you would want to kind of then find the actual track, right? That makes somewhat sense. Like similarity, perceived similarity is high, but they did not find that. So we have on our GR to like, should we have invariants for speakers and microphone in poll response things? Maybe to facilitate that use case. But the product feature thing sounds obvious.
Great, would be nice
Yeah,
to see that.
it's pretty cool.
We have some question also from Andjed. What are some reasons for or against choosing TensorFlow over alternative frameworks like PyTorch?
I'm not really aware of the answer because I'm on the ops side, operations side, and the decision maker for this is R&D team. But in a general view, TensorFlow is more Google Cloud friendly for us as well. So it makes sense to choose TensorFlow and TF serving over, for example, PyTorch.
Sorry, could you speak up a bit?
Yeah, sure.
You can come closer to the mic because it's here.
Let's stand.
Okay.
Maybe you can say again. Yeah.
I said that I'm on the operations side, so I'm not exactly aware of the reason, but from what I know, developing and deploying the model that is built in TensorFlow is easier in a cloud, in the Google Cloud platform, at least for us.
Okay, and I think I have a related question actually. So you mentioned you use Google Cloud for the play testing platform. Are you using or considered using any of the machine learning services provided by Google, like Vertex, for example?
Not yet, but we are currently studying the domain, and we are assessing the third-party tools, different ones. And we are trying, as I said in the beginning of my presentation, we are looking for a good solution for an end-to-end machine learning platform that fits the requirements of our organization.
Good luck with that. Tell me when you find that. Let's have another talk.
As
Also,
Carl
Vertex
said,
sucks.
we are looking into Vertex.
Yeah.
No? Okay, good to know. Yes, this is very interesting. How big is the team that works in this productification project, and how long have you been working on this?
The team, ML R&D, is changing. Its size is changing over time because we always have interns coming and leaving. But generally, it's about 8-9 persons. And the MLOps team that is recently shaped. Currently, we are just 3, but we are, as I mentioned, hiring. We're looking for colleagues.
Cool. You mentioned in the end taking care of the data pipelines and metadata. What is a good tip for taking care of the data pipeline and metadata? Do you have any design rules for data?
Design rules for data. I brought up an example of our ETLs, and as you may have noticed, we have a complete separate independent component in our SDK that is in charge of our pipelines. That's the main point. There is somewhere that keeps track of the pipelines, and we are monitoring them always. And yeah, these are the basic practices of data engineering. At the beginning, those basic practices seems good enough. Maybe you have more complex use cases, it's a different story. But for normal training, testing, bringing the data, cleaning the data, and preparing it for training, yeah, it's regular pipelines that just you need to be aware of them and keep in mind that this is important, and this keep account for this part of project. It's not something that is happening somehow. It's a big task. It's an important task in the project.
Yeah, I agree. How well do the bots resemble human players?
What do you mean by how well? But well
I don't know.
Well enough, because for example, from the outcome of the tweaked levels, we can somehow infer that players are more engaged with the levels, or they are more happy because after tweaking all the levels, we collected the feedback, the data that came to us, and we are trying to compare those outputs. So it really works, and it looks like human. There are some edge cases, for example, very hard levels or peculiar objectives for the game that are more tricky, but so we are right now looking and trying to, for example, one path is to train models for different types of objectives for the games that are aimed at collecting the scores or collecting those cherries, or for the games that you need to just free the beers for soda. There are different objectives, so it makes sense to have a bot specific to those kind of objectives to make it more accurate. But in response to that question, I may say well enough.
Okay. Great. And I have, I think, one last one. How has the game teams improved from the testing? Better levels, more levels, other?
I didn't get the question.
Neither did I. But I guess I don't know if the levels changed and you added more levels, or you changed the levels, or was there something else that it was improved after or from the testing process? That's how I can interpret that. Or if you can write some clarification.
I can try to explain it. I just wondered, now having this AI testing, what has the benefit been for the game teams? Have they become more efficient, so they produce more new levels, or what has happened? What is the benefit of the AI testing?
Sorry, before you answer, I'm going to repeat it so that and make sure that that people online have answers. So, what is the benefit of the AI testing for the teams? Are they being more productive? Do they create more levels, better levels? This
Yeah.
is the question.
I think the most important point is that they can check and make sure that the levels conform to their design guidelines. For example, there are KPIs that measure how good a level is, how fun is it to play, and they can go back, find the levels that are not fun, tweak them, and put them back. So this way, the whole journey will improve. And on top of that, new levels would be approved more quickly. The process will be more efficient.
Good, but I think that is all. We have answered all the questions. So thank you very much for today. Thanks everyone also online. One thing before you go, please answer the feedback questionnaire in Slido, so you can just log in again and answer the questions. Tell us what did you think, what we can do better, especially in this kind of hybrid sessions that we have, like online and also people attending in person. That will be super good for us to know what to do better. And thanks for your presentations.
It's great. Thank you.
Thank you.
Mm-hmm.